Welcome again for the second part of our workshop. So we will have two keynote talks in this part, and we are starting with Dr. Julian Kooij. So he's from Intelligent Vehicles Group from TU Delft. And I think we can start.
Hi. Yes, let me share my screen. So thank you for this invitation. And I'm also going to share audio. Can you see my screen?
Yes.
Perfect. So yeah, great. Thanks for this workshop and thanks for inviting me. I wanted to present some work that we are doing in our group where we are looking at different sensing modalities for intelligent vehicles, different from what are sort of the typical sensing modalities, where we're taking data-driven approach, and in particular towards acoustics and low-level radar data. Let me see if I can, yes. So most data sets that we are using in vehicle perception are focused on images, video, and lidar point clouds. And we are all, I think, very familiar with these data sets, these benchmarks that are used everywhere, like the cityscapes and new scenes in the University persons data set. But these are all vision data sets, some lidar data, and very few data sets contain radar. I think maybe new scenes contain some radar data. But overall, we see that there's a lot of research and data focused on this side of the spectrum and very little on these other sensing modalities. And we can see that radars typically address more with signal processing techniques and modeling assumptions rather than data. You could even wonder what's beyond this, right? Maybe there are other sensing modalities that we are not exploring currently because we're so focused on the vision and the lidar data. So I think it's interesting to take a look at on this side of the spectrum. I'm not sure if you can see my mouse. Let me use a laser pointer. So I'm interested in seeing what's also on this side of the spectrum and if we can use insights that we get over here and these data-driven techniques on this side of the spectrum. So in particular, I will be looking here at work that we did on the low-level radar cube first, and also on acoustic perception in the second part of the talk. And in between, we'll also take a very short look at some sensor calibration. But overall, it's interesting to explore what kind of novel and complementary information that we can get from these low-level radar information and from the acoustics that conventional sensors cannot provide, right? So it's not really intended to replace all the traditional sensors, but we're looking for new types of information. And the data-driven direction is appealing because it allows us to become more robust to real-world conditions without relying on very strong modeling assumptions, as is more conventional in the signal processing approach. And to do this, we also need to benefit from multimodal data collection with our own research vehicle, such that we can, for example, use the existing modalities and existing detectors in order to create annotated data for these other sensing modalities. So for the first work, we'll focus on the low-level radar, where we are interested in doing road user detection, so not just vehicles, but also pedestrians and cyclists. This is work by our PhD Andres Palffy in Jiaodong, was a master's student with us and has been published in RA-L and also presented at ICRA. So if you take a look at the conventional automotive radar, it provides normally a sort of a 2D point cloud, which is pretty sparse. And 2D as being in the plane in front of us, right? We have the azimuth and the range. And for each of these points, we get, so its position in front of the vehicle, but also a radial speed, the Doppler value, basically, and some reflectivity value, you could say, the radar cross-section. So we have 4 values for each of these points, and overall in a very sparse point cloud, because if you project it back to the camera to visualize what we're seeing here, you can see that this cyclist in front of us might only have 2 detections at a single moment. And traditional techniques that work with these radar point clouds, they take the radar's input, provide, this is done by the OEM, by the radar itself. It provides these sparse points. And the first step that people typically do is that there's some clustering involved. You try to figure out which points are probably together part of the same object. And then based on some statistics of the clusters, you make some classification. For instance, you're saying this is a small cluster, or these points might be on a line, or there's some structure in the cluster. You use some statistics that you extract in order to make a classification that this cluster was probably a vehicle or maybe a cyclist or a car. And if you know the class of this whole cluster, you would also know what the class is of these individual targets that are within it. But you see that you basically first try to identify what's the whole object, and then you get an idea of what the individual detections were, right? So the clustering comes first before the classification, this traditional pipeline. But that can lead to some challenges. For instance, if you have both objects that are very big, like vehicles or trucks, but also very small, like pedestrians or cyclists, you might, if you first cluster and you don't know really what you're looking at, you might cluster some objects together that are small, like these pedestrians, because they're so close together, and say, well, this might be one structure. Then afterwards misclassify this as a cyclist or a car. On the other hand, bigger objects might be missing some intermediate detections. You might split them up and over-segment them, and therefore think that these are maybe smaller objects like a cyclist or a pedestrian. And what do you do if you have only a single detection? You cannot really compute any cluster statistics on this single detection, so you might easily miss small objects. So what we are trying to do here in our work is to reverse the order of these 2 main processing steps. So if you would get the targets, we are interested, can we first maybe classify the targets? So get a class label at the target level, and only then cluster them, where you can consider each of the type of classes independently and take into account that pedestrians are smaller and you would less quickly cluster them together in big objects. While for cars, you might want to be a bit more robust against gaps in between the objects. So we've turned these 2 steps around if you compare to the previous conventional method. But to do this, we also need additional information to do this labeling of each of the targets. And for this, we take a look at a byproduct that you typically don't get out of the radar, or maybe actually the targets are based on this low-level representation, which is called the radar cube. We are going to use the radar cube together with the targets that we get from the signal processing to improve this detection. So what is the radar cube? If you have the range angle, this 2D plane in front of the vehicle, the radar cube is actually a discretized representation of this space, but also with a third dimension, which is the velocity or Doppler range. So you get this 3D tensor that tells you for 2D spatial locations what is the underlying distribution of speeds that you would find at that location. And this is useful information, especially if you look at pedestrians and cyclists, because they have a lot of different moving parts, limbs. And it's well known that if you have a pedestrian that is walking, that these different speeds, they provide different responses in your radar. And here you can see over time, for example, somebody is walking away from a radar, and this is the time axis. You can see that in the Doppler spectrum, you can actually see all these different body parts moving around. So this is a very precise micro Doppler. We don't need it this precise. This is if you're standing still with a very accurate radar. But you can clearly see that these patterns can be picked up by a radar signal. So we're interested in using these speed distributions as they provide us information of the particular object that we're looking at a particular location, specifically pedestrians or cyclists. So our approach is to take this radar cube and also the standard targets which have been processed, and we use these targets because the radar cube still has some ambiguity, some reflections in here, as you can see here on the right. This spot, it's also here on the left, but the targets are much more robust to these reflections. So we can take a look at these targets over here, and then we project it basically into this radar cube and look up what was the Doppler distribution at that particular location and its surroundings. So what you can see here is the camera view, just to get an idea of where these radar targets would be here on the bike, and the overall reflectivity measured in the radar cube. And here you see the cube in 3D again. So at this particular location of these targets, there's this distribution in the range, velocity range, that you can crop out for each of these targets, and you get this column of very local range azimuth and then a velocity distribution. Well, we feed this 3D tensor into a convolutional neural network together with some the information that we got from the target level detections, and we use this to classify each radar target either as pedestrian, cyclist, car, or some other object class. And once we have classified the targets, we can perform the clustering, which is done, as I've said, in this class-specific approach. So what you get here is then a proposal that's consisted of putting all these detections together. Now, how do we train such a detector? That's one of the challenges if you come up with such a new idea. You need access to a radar that provides you this low-level radar cube information, this target level. So here we work together with Conti. But we also needed our own vehicle to collect the data. So we drove around and we collected data with this radar. We have, of course, IMU and GPS and stereo camera information here. And we try to use, we successfully used the visual object detector based on the stereo camera to detect the objects in the view and then back project these through the 3D space using the stereo point cloud. So this assumes that we have sort of a well-aligned camera and radar system, that we know exactly how they are positioned relative to each other, but then we can rely on the detections from the camera to provide us with annotations for the radar. And overall, by just driving around for an hour, we actually got quite a lot of pedestrians, bikes, and cars. So the Delft inner city is very densely populated with pedestrians and bikes. It's a Dutch urban environment. We have a lot of bikers as well, and people walking around. But you can still see that the majority is pedestrians. We still have a lot of parked and driving cars and buses, and still a fifth over here are bikers. So I will go a little bit more in the next part on this calibration, but to get an idea of the kind of data that we have, I hope this video is working. Yes, here we go. Here with our lidar, our Velodyne, and these are just the low-level radar detections. Our stereo camera view, you can also see detections here as bounding boxes. I hope it translates over the zoom of cars or cyclists or pedestrians walking around. So this gives a bit of an idea of what our processing pipeline was to collect the data for our radar method. So we can then evaluate our method based on how well did we classify each of these individual radar targets. And here we compare to two of these conventional baseline methods here in the top and our full method here in the bottom. And you see that the benefit is small, actually, if you look at the target level. What you can also see is that our data-driven approach, where we use the radar cube, it really benefits from having the low-level data. Because if we drop out the low-level data, as you can see in these four options, which try out different variations of our methods. If we drop the low-level radar cube, there's a big reduction in average performance. So we really benefit from this low-level data. But you see most of the benefits when you go to this next step, to the resulting object level detections after you've clustered. because then our method really shows that it performs better on average, much better than the existing methods. Right. So without going into too much detail of all the quantitative results, I think it's useful to get some idea of the qualitative results. So here you see single frame radar only detection, right? So with a camera, you would be able to detect these objects, of course, as well, but we're just using it, looking at the radar, at these dots. And the question is, do they have the right color? So here we classify them as pedestrian, cyclist, or car. We're not showing the non-class of static objects. And the benefit is that if this works, you can also do it, of course, at night. So here you see nothing with the camera, but if we turn on the headlights, you might see that there's actually a cyclist over here and there's a pedestrian walking over there. And we're not really misclassifying this as vehicles. So there's really a benefit of having this night vision using the radar. And if you look at the object level detections where we've clustered them together, you can see we can also deal with buses, pedestrians moving behind, cars. You still sometimes see some misdetections. Again, there's no temporal information included here, but this is purely radar based. There's also some smoothing that might be needed, some tracking, of course. But overall, if you compare it to the existing methods, because we do this clustering afterwards, because we've exploited the Doppler information early on in the classification stage, we are less prone to make these type of superclusters where we undersegment or oversegment big objects into smaller objects. Well, to do this data collection, we had a small intermediate challenge. Well, not that small actually. That's that we had our own. We have our own vehicle. We are a small research group, and we need to have all these sensors aligned. So I shortly want to mention that we have some work on this published and also some code published where we use the ROS framework. And we basically created a design, a pattern that can be detected in both radar and lidar and stereo camera. And we have published detectors that can run on your own ROS nodes to detect this board, and you move it around, and we optimize the positions, the extrinsic calibration of all these sensors together. So before calibration, there's a lot of misalignment, and the alignment gets really good after the calibration. So as a video, we've moved the design around, and you can see there's a good match. But what we now have are the coordinate systems of the lidar, of the camera, and of the radar. But we don't really still know how they are relative to our own vehicle, right? They're only sort of relatively calibrated to each other, but not to some absolute base of our vehicle. So that's what we did in our next work in the transactions in intelligent vehicles. We explained our approach to make this also work well with for absolute calibration, where we want to know how these sensors are aligned to the vehicle base, which is defined as the back axis of the wheels on the back of our vehicle. So for this, we also use an external Leica laser scanner that would provide us, as we were moving around with the point cloud, also with a very detailed point cloud of our own vehicle together with the calibration sign. So we could use the same method actually to detect where the calibration sign and the calibration board was with respect to this dense point cloud. And then if we know where the calibration board was with respect to the sensors, and we can find where the wheels are in this dense point cloud, we have basically calibrated the whole setup. So we looked at some different ways of doing this. The details are described in this paper. But this is how we got our whole sensor setup calibrated relatively, without a lot of pain, so to say. And one thing here to note is that it's interesting to see how would you assess that such a system is well calibrated, right? How do you know that the calibration worked? We found that actually the most challenging part was knowing if the whole sensor setup is not rotated slightly. So if here on top of the vehicle there's the lidar sensor, our thinking was that if we would be driving along a straight road, if the lidar would be slightly rotated by a small degree here, actually at a big distance in front of us, that would shift the whole point cloud. And if the lidar shifted and all the other sensors are well calibrated, that also means that the stereo camera and the radar are not really well calibrated. So we focused here on the lidar and tried to assess, is the lidar well aligned with the moving direction of the vehicle? And to do this, we drove along a road with a lot of light poles on the side of it. And our idea was that if this coordinate system of the lidar is well aligned with the car, if we move straight ahead, then the lateral position measurements of these poles should not change over time. So it doesn't really matter where they are, but we should have the same lateral measurement along the y direction of these poles as we move forward. So over time, you would expect to see these measurements to be the same. So these horizontal lines. And if there's a small angular offset, then actually you would see sort of a drift in the lateral position, right? So that would be like in these red lines. So indeed, before we calibrated it, the whole sensor setup with this extrinsic absolute calibration, we did find we did have some drift. So here are a lot of these poles as we drove around. And after calibration, this angle, if we fitted a line through these measurements, was almost completely gone. So I just wanted to share this idea. If you're wondering how do I calibrate my own sensor setup, this is how we did it, and this was for us the biggest question. How do we get this angular? How do we assess if our angular error is been reduced? Now, let me take a quick look at the time. For the third part, I wanted to take a look at acoustics. And this is work that's been published very recently in our RA-L paper in 2021, which I did together with Yannick Schultz, Avinash Matar, and my PhD Thomas Heng. And I hope you can hear the sounds. Maybe someone from the organization let me know, can you hear it? Is this sound?
Yes, we can hear it.
Yeah, perfect. So we were interested in this situation where you're driving around and especially in urban environments, maybe not in the highway, but in urban environments, you often don't have a very clear view. So as in this, going through roads, you don't see if something's approaching. But because of the sound, you might hear it. So we are so focused with the camera and the lidar, and to some extent also with the radar, on what we can see immediately in front of us, that we're not really used to thinking, also maybe as car drivers, about what kind of information might be there that can anticipate situations that we cannot really directly see. So in these kind of case of blind corners, our view is very limited and obstructed by buildings or maybe other obstacles. But we can still hear it, right? And the sound might give us information that at least something is approaching, but even maybe where it is approaching from. So our idea was to figure out, can this be done in a real setting? So some related work has been done in that direction. I found some work back in 2012 where people tried to do non-line of sight, so occluded or obstructed sound source localization. But this was done in a very lab environment with a single microphone, and it's also very much focused on a signal processing based approach, right? So you try to model all the variables of the whole system and then try to retrieve, do I know where the sound is coming from? And it was not very successful. Well, more recently in the robotics community, 2018, there was some work on using speaker diarization. So trying to figure out, if you have a room with people speaking, who is speaking and where are they around me. And this work showed as one of the first works really that you could use deep learning based on low-level signal processing to immediately regress or predict the locations of these speakers and do a classification at the same time. So this is already much closer to what we're interested in, but it's in very controlled conditions inside, not really outdoor conditions. And in ICCV in 2019, there was a work from a group at MIT with 2 microphones that looked at images and at the same time tried to use the stereo microphone to also predict the presence and location of a vehicle. But this was still in line of sight, right? So you had at the same time, you saw the vehicle and you tried to hear it, which is different from what we are trying to do, is where we're trying to hear something that we cannot see yet. So, and where it's not line of sight. So the benefit of having our own vehicle is that we could just go wild and bought a 56 microphone array from a company and mounted it on top of the roof, because why not? Clearly, these are not really intended as a actual system where you would drive around like this, but this is our research prototype to investigate what are we actually measuring and how good is the quality, right? You can imagine if you have 56 microphones, then you can also always test what happens if I have only 2 or 10 microphones. But this gives us the most high resolution result to study the effects that we're interested in. The microphones themselves are pretty small, and you see over here is our stereo camera setup, so we had everything aligned again. So the same situation where there's this car approaching, but we're now looking at it without moving ourselves, reduce the number of variables in this setup. So now it's just the other car that is moving. And if you look at the situation, you use all these microphones, you can perform beamforming, which provides this pattern of where does the sound come from, where do we measure most sound intensity. What you're seeing is that as soon as the in line of sight, then this clear sound intensity spot follows the vehicle itself. That's the most direct angle. But before that, you see that there's actually reflections over here. Reflection on the left side of the building and also reflection in front of us. And these patterns are very indicative of where the vehicle's approaching from. So our idea is, instead of modeling the exact propagation of sound through the environment, we can treat this as a pattern that we want to classify. So instead of 2D, we do this actually in 1 dimension in front of us. We take all the microphone information. We perform short-term Fourier transforms, sort of standard processing techniques that happen in acoustics. And we look at sort of the main frequencies that we are interested in, sort of the frequency range of cars, not the very high pitches, and then divide that into from 1 second into 2 half-a-second splits, so we get some sort of temporal information out of it. And then for each of these half-second splits, we perform a basic direction of arrival signal processing technique. So that provides us with a distribution around the vehicle. Where does the sound come from? Similar to the images that we've just seen, but those images also have elevation, and here we don't compute the elevation, so it becomes like a 1-dimensional histogram. And then we have, for these 2 half-a-seconds, this becomes 1 feature factor. We concatenate these 2 distributions together, and that we feed into a classifier where we're just trying to figure out, is the vehicle approaching from the left, from the right? Is it in front of us right now, or is there no vehicle approaching? So those are our 4 classes. And when we test it, we can run this in a sliding window, running classifier over the last half-a-second, where we're using we've looked at different kind of features, but we're using some basic, well-established direction of arrival features as input. And in the end, we ended up using a simple support vector machine classifier, although we also tried more fancy stuff like neural networks, but it didn't really matter that much. So again, we had to do some data collection in real world environments because of the safety involved. Because of this, we have a very limited vision. We did this by driving the other car ourselves for the most part. Sometimes we had some other cars passing by and we collected those as well. But it was in outdoor conditions, but we tried to reduce the number of variables. So we had only 2 types of environments, one which was fully closed off with buildings, and the other type of environment where there was sort of an open space in front of us. And we collected its data while our ego vehicle was standing still. not moving, but also when it was driving. So we also have some sequences where we collected where our vehicle was approaching the intersection. You can see here the total number of recordings of samples that we have from each of the classes. And we annotated the last moment before the vehicle became visible, sort of our T0 moment, our moment of where we had to make a decision. Well, we evaluated our methods with a lot of different, again, choices in the hyperparameters. We studied what do we need to do. We also checked out some forms of data augmentation. What you can see here, here's our proposed method, the overall accuracy that we had in predicting the 4 classes. And this worked really well on the static sequences. Here were the different variations. We picked this one in the end. It had the best result, but you can see that the other choice of the SVM didn't really impact the overall accuracy that much. And we also looked at what happens if you just do signal processing. You just take the best response. Well, that doesn't really work because, as we've seen, it's really the reflections that might give you a signal in a direction in the opposite direction of where the vehicle is approaching. So you really need to take into account those reflections. We also took a look at what if I would have just used my camera to detect the vehicle. And then, of course, you would be really good in detecting the vehicle when it's in front of you and when there's no vehicle, but you wouldn't be able to detect the vehicle when it's on the left or the right, still behind the corner. So this is not really surprising, but it highlights that what we're doing is not something that could be done visually. We can also take a look at the detection confidences over time. So here at moment 0 is when the vehicle first becomes visible. And here in green, you see the prediction when that our method is predicting that the vehicle is approaching from the left. And in red, the probability that the vehicle is approaching from the right. While here you can see it was indeed approaching from the left. So in these recordings, in these situations, the confidence keeps increasing that we are approaching from the left. And then it changes into this blue class, which is the front prediction when the vehicle is in front of us. And the same pattern we're seeing here on the right. And when there's no vehicle approaching, we actually keep a high confidence that there is no vehicle in front of us. And this means that with our visual baseline, how we could detect the presence of a vehicle, overall 1 second before it was visually possible, right? So also the visual baseline cannot detect the vehicle when there's a single pixel of the vehicle visible. It needs to be the approaching vehicle needs to be passed behind the corner a little bit before it can really detect it. So overall the difference was about a second. We also tried it with the moving vehicle, and that worked in some environments. So in some regions we got pretty good accuracy, but in the other environments it was much more challenging. But we have to say we also had here more data because of the moving, the ego motion, the patterns become more complicated. So this is still an open issue. We also found that it doesn't really generalize well to these different environments, like these type A and these type B environments. So right now you need to classify 4 particular environments. So this is a direction of future work. I wanted to end here with some examples of the classification working in real time. As we are here first standing still, you can see here the prediction, the main prediction. Here you see in the top left the confidences of the different classes. And here in the top right, you basically see the direction of arrival patterns that we are feeding into our classifier. So here you can see really the reflection patterns that we are trying to classify. And I hope this really illustrates that the acoustic information is really systematic, right? It has a very clear pattern that you can pick up, and that you don't really need to fully understand as long as you can classify it in this data-driven approach. Here's another one. Here's the type B environment, where there's some open space in front of us. And finally, also when we're driving, notice early on already the vehicle to the left. So overall, there's still much more work to do. You want to base it on this local environment. Like we've seen, there's differences between the type A and the type B locations, and there are of course many more type of locations that you would want to be able to deal with. And you would want to be able to classify many more different sounds and also focus on multiple targets. We have here looked at one target at the same time. And we want to do a bit more than just classifying. We want to know how much time do we have before the car is, this approaching car is in front of us. But overall, I think the biggest bottleneck here is the data, right? How do we collect the data in an efficient way that we can scale this method up to many more situations? And I think this is the overall conclusion of my full presentation. As well, that there's a lot of information that we're missing out on because we're focusing on the vision, on the point clouds from lidar. But we might want to think, is there not more information in the low-level data from the radar or from acoustics that we're not really used to think about, but that provide complementary information about the traffic situation? But to do this, we need to move these methods away from purely signal processing to a more data-driven approach, so that we can make them robust to the actual physical and environmental conditions and not rely on very strong modeling assumptions. And for this, we need some better ways to collect the data, but also better ways to make it robust, and to not rely on strongly labeled data, but use this easily collected unlabeled data, right? And the modality can be here a real benefit where you can use some sensors to annotate the other sensors. Okay, thank you very much for your attention. I hope I'm still within the time. Are there any questions?
Thank you, Julian. Yeah, it's interesting to see that there today we have heard many approaches using acoustics. I think we have already some questions. So, Max Portcourt, you can go ahead.
Okay, thank you for your presentation, first of all. I have two quick questions about your multi-sensor calibration. Is it necessary to move the calibration board around during the calibration? Or, for example, does it have to be stationary so that it can be seen by all the sensors all the time?
So can you repeat the first part? Is it necessary to
move the calibration board that you used, like the chessboard pattern?
Yes. So it definitely helps. I would even say it's necessary, especially for the radar, because if you look at the calibration board, we have a single corner reflector here behind it. So for the radar, we get like a single point, and you want to get, so you would know where the board is in the radar. You get one location, and you would know where the board is in the other sensors, one location. You would need multiple locations to really constrain this problem, right? And you can, well, how many locations do you need? I think 4, I guess, as a minimum. But the more you get, the better you average out the error. And in fact, you would want to need to do this not just at this short distance in front of the vehicle. You would want to move it further away as well, right? I think this is the same as what you do with calibration with the camera, where you have like a chessboard. You want to move it around a lot, especially in the area where you think you will be operating with these sensors. So at those distances.
That makes sense. Thank you. For the follow-up to that, is it possible to select certain combinations of sensor pairs? For example, only lidar and camera sensors in this calibration package?
That's a good question. So I haven't had my hands-on experience with the tool in a long time. So what we did, it's definitely modular. So there were some calibration tools out there already. And what we found is that most of these tools, they were very built for a particular setup. So what we have done is that we have implemented these different detectors as different ROS nodes. I think we can also run them offline without the ROS. So the ROS was only a wrapper if you would want to use it for each of these sensors independently. So for each of these sensors, you can detect where the calibration board is. That means you can also have multiple cameras or multiple lidars in principle, or multiple radars. And then all those detections are fed into the optimizer that provides that solves the problem. So here's the question. I think it was done via configuration file, but this is something to check out on the GitHub link. And then the final step is that we update the URDF of the vehicle. So that's also done in a modular way. So it's not really specific for our sensor setup.
Okay, that's great. Thank you.
I have also one question,
Sure.
Or even two. Thanks, Julian, for your presentation. In the beginning, you talked about this data set and also about the camera, lidar, and radar. In here, I think in the beginning on slide 7, you mentioned this over-segmentation problem, where you detect multiple objects, given one object, this over-segmentation problem here. We have a similar problem in our project where we perceive objects on the highway, and if we have long objects like trucks, you also get 2 detections from the radar. And how do you solve this problem?
So, well, our solution here was by turning around this problem, right? So here where the conventional method was first clustering and then classifying. So that means that you don't really know you have no idea of what you're looking at when you're doing the clustering and when the segmentation occurs, correct? So if you know that you're looking at a really big truck already, the clustering parameters, which might be something like dbScan, you have these parameters, hyperparameters that tell you how much space do I allow between the clusters, or how big should the cluster be. Yeah, you cannot really make any assumptions on it in this setup, in this conventional setup, because you don't know what you're looking at, right? So you have to make sort of a choice that is okay on average, but which might not be optimal if your object is really big. It might not be optimal if your objects are really small. So our point was, or the way that we addressed it is, if we first try to get a good idea of what these points are, what we're looking at, then we, for example, pick all the things that we think are truck, we can adjust our clustering on parameters that are suitable for trucks. And then knowing that we are looking for really big clusters and that there might be quite a big gap between the points within the cluster. Does that make sense?
Okay, got it. Thanks. And I have another question about the data set that you labeled, where you included radar, camera, and lidar. And did you also label the height, or?
So I simplified a little bit because I showed you this video, which has the lidar. We did not have the lidar on top in this data set, but I thought it was just easier to explain it with everything inside. So here we had the radar, the stereo, and IMU and GPS, but not the lidar on top. But so there are a few different data sets here in play.
Okay, what exactly did you label here in this data set?
So in this data, we labeled manually very little. I think the PhDs he double checked it. Maybe he corrected a very few small things, but he did this automatic annotation by using our stereo. So we are working here in line of sight. So what we're seeing in our radar is also in view. And with the object detector, which is very robust, and we also only collected here the data for training in sort of daylight, good conditions, so we could really well detect objects using our stereo camera. And because of the stereo, as you've seen in this video, we can back project it into the depth, and that worked. Yeah, it doesn't really work very far away because the error of the stereo keeps increasing, of course, further away, but at least nearby this gave us sufficiently good detections to train the method. So we still have an open question: how well would this have worked if we would have done this manually, right, with the lidar and really make really proper annotations? This is something that we're still looking into, also maybe with some labeling company, but well, I think you also know, with the labeling tools, there's sort of this gap that we don't have yet, a sort of really reliable method, or we didn't have a reliable method available to annotate all of this manually. So this is why we were very interested in looking, can we just not use our other sensors for which we do have more or less reliable detectors? I think in the end you would want to have a combination of both, right? You want to use your reliable detectors where you can, from vision or maybe from lidar. and then correct them manually afterwards. So we didn't do manual labeling here in the end, except for double checking.
Okay. And did you also try to fuse data from radar together with lidar and camera?
Yeah, this is also an important research direction. It's not something that we did in this work. So the videos that we've been showing with the camera was just to double check what's happening here, right? What are we detecting? But this is purely radar based. So what we do in fusion is normally late fusion at the object level. You get objects detections from lidar, from camera, from radar, and then you fuse that at the tracker level. But I think an interesting direction is how to fuse this lower, right? Or learn how to fuse this, so to say, and extract this information jointly.
Okay. And I think I have a small question about the last part, the acoustics.
Sure.
Does it also work with low-cost sensors, for example, like a microphone from the smartphone?
I have not tried a single smartphone, but these sensors here you see, so it looks really daunting, right? It was a prototype research array from a company in acoustics that I contacted, and I said I want to put this on a car, and they said, well, we've never done this, so I got this this weird big thing. But the microphones themselves are actually very low cost. They cost $1. It's this little thing over here, and then you have, of course, this is to reduce the noise of the wind. In our RA-L paper, we also have some qualitative results, by the way, that I did not show here, where we're driving around on the road in sort of 50 kilometers per hour. You can really see that even when there's a lot of wind, because you have all these microphones, you can really filter out the noise, the background noise, and really get spots on each of the cars that are approaching us. So I think you can use these low-cost microphones, but what we found that really benefits is having multiple of them. Not 56, but already with 7 microphones and more or less front-facing, they really help in canceling out the noise or filtering out the noise, because you're comparing these signals together and get good beamforming results. So I think in the end, a more realistic setup would be to have along the top of the car, have a line array of a few low-cost microphones. This is sort of what I'm interested in, and maybe also on the back of the car, because we're right now not really distinguishing between front and back because of the symmetry of this of the plane, how it's located like this. So yeah, I definitely think you can use low-cost sensors, but at the moment there is no real automotive solution, and I think this is a very open research direction still. We're just not used to thinking about acoustics in intelligent vehicles. Is my opinion.
Yeah, really interesting. Thank you.
Yeah, I also have one question related to this last part. Here you show the results using acoustics only and compare it with vision data. Do you think it's meaningful to fuse these two information coming from vision and acoustics for this task?
So absolutely, I would not, or I would argue that you would need all. I would argue that you need all sensors. So I'm not arguing that you need acoustics instead of vision. Vision is really robust and works really well. But I think the acoustics can do things where neither vision nor lidar can work, right? And that's the point of what we're showing here. It's not that acoustics is an okay method to detect objects in line of sight. It can work when it's night or when it's very misty, maybe. But our point was to really show you can detect objects when it's impossible to detect them with vision. Although you might maybe think maybe there's some reflecting window. If you're driving a car, sometimes you see in the reflection of a shop window, you can see something approaching, right? I think there's some works that we're looking at shadows of objects approaching. And there's also work that we also cite, a very recent work on radar. So radar also has some of the reflective properties where it can bend around corners. So radar might be the one candidate that can do something something similar. But I think it's, especially for these cases, acoustics has an edge. And if you drive a bicycle yourself, you're very familiar of perceiving traffic around you using your ears. I drive a bike myself all the time, and I always know what's going on around me because I'm hearing it, right? And I think this is something where acoustics can really benefit or aid vision, But once it's in front of you, it was also in the quantitative results, then vision is still king, I would say. So definitely fuse both.
Thank you.
Maybe I have one final question. So about the temporal processing, like for the tracking, for example, can we or how accurate the Doppler velocities of the radar points that we can maybe project them to the upcoming frames?
You're talking about the first part. How accurate
Yes.
can the Doppler radar points?
The velocities that maybe we can use them to have more points from the objects in the upcoming frames.
Ah, I see. Yeah, yes, definitely with the fusing. We're looking also at some newer radars, and it's a similar trick that's being done. That's typically being done in lidar as well, where you try to accumulate a few point clouds over time. You get a more dense representation, and the Doppler can help. So a problem is with the Doppler, there's still some uncertainty around it, right? So you have the radial speed. That means for this point, you're measuring from your vehicle how fast is this point moving away or towards my vehicle. So it's one component, but it doesn't give you perfect prediction of where this point would be in the future, which is the lateral speed in this case. So it does help, but it still has some degrees of freedom that you need to solve. So the naive way is just still putting all these points together. For a lot of static stuff that works quite well, or when the speed of the other object is relatively static because you're moving at more or less the same speed, then that's not really a problem. And then that's trick works, but just as the same way as the lidar works, not really because you're using the radar. Otherwise, you would need to do some tracking and some assumptions of what is the object doing over here, right? So you're using more temporal information to fill in the gaps, and I think then that could work. But we still make here very strong locality assumption when we extract this radar cube information around our current point. So at that point, you already need to know what belongs together, so to say. I think there's still much more work here to do, because there's a lot of variance with these radars, and much more variance than you have with lidars and cameras, I would say. So there's more to explore.
Okay, thank you.
Thank you.
I guess so. That's it. Yeah. So we can move on. Thank you, Julian, for the nice presentation.